we continue discussing isometries. So that's lecture 2.2, and that's about rotations. So rotations are very important isometries where you take some point and rotate the whole plane as a whole. So definition. So you take point O inside R2, and then rotation around with the center O by angle phi is a map from R2 to R2. Defined in the following way. So R O phi of x equal to y when oriented angle from x to O to y equal to phi, and the distance between O and x equals to the distance between O and y. And this is kind of an oriented angle. So let me try to explain what I mean here. So let me choose maybe this point, this point O is here, and then I choose a certain angle phi, and I choose not only just the angle as a number, an angle as a kind of geometric angle, I choose a direction. So it's very familiar in trigonometry where you consider sort of angles on a circle, and they can have arbitrary real number as a value, and you kind of go counterclockwise by this number of radians. And so I fix this phi, and then what I do, I take my point x, and then I take an array starting with O and going in certain direction where the angle between the rays is phi, and then I find a point y which is on the same distance from O and move. So this is what RO phi of x is, and it's a simple exercise, more or less trivial, that if I rotate by phi1 plus phi2 with a certain center, that's the same as rotation by phi1 composed with rotation by phi2. And actually, if I rotate by the angle 2 pi, okay, that's the same as rotation by 0, which is identity. So if you rotate by 2 pi, that's the same thing as not to do rotation at all. And that's very simple. And then, so let's see that RO phi is an isometry. And for this, it's enough to draw a picture. So the picture is as follows. So we have O, we have x1, and we have maybe x2. And then we move by certain angle phi, and this is where x goes, and this is where, that's y1, y2, where x2 goes, and the distances are like this. And then we see a pair of equal triangles. So triangle, let's see, so x1 goes to y1, x2 to y2, so triangle x1o x2 equals to triangle y1 o y2, and because they have two corresponding sides, and also since these two angles are equal, these two little angles are also equal, and then we deduce that the distance between x1 x2 equals to the distance between y1 y2. So we see that rotation is an isometry. And by the way, another important maybe example is that if I do a rotation by angle pi, that's just the same thing as central symmetry. So central symmetry is a special case of a rotation. Okay, so what about rotation in coordinates? So let's see. So how shall I do that? So maybe the easiest way to do it is first to consider what rotation does with vectors. So what is that? So for this, let's take coordinate plane, and let's write coordinates axis exactly with the center in O. And then we can take a vector E1 and a vector E2 where they are perpendicular vectors going along x and y coordinates, and I can think of a vector E1 as having coordinates 1, 0, and E2 having coordinates 0, 1. And the question is, what does RO to the vectors E1 and E2? So I can compute it, that's not hard. So RO of E1, so for this I need to rotate my vector E1 by angle phi, R phi, and this is obvious because I need to compute coordinates of a unit vector having angle phi with the x-axis, and that's exactly how we define cosine and sine in trigonometry. That's cosine phi, sine phi. And then if I do the same with E2, then a simple exercise is basically that it's the same as rotate E1 but by pi over 2 plus phi. And so this will give you minus sine phi cosine phi. So this is where these two vectors go. And what it means that if I do a rotation with the vector xy, so this is the same as rotation with a vector x e1 plus y e2, but an exercise before says that, so when I do this map with a vector, this one is linear. So I can write it as x RO bar of E1 plus y RO bar of E2, and that's x cosine phi minus y sine phi, comma, x sine phi plus y cosine phi. And that's very convenient to write it in the matrix notation. So that's a matrix cosine phi minus sine phi, cosine phi. And I multiply it on xy, and I get this vector written as a column, though. So that's this one is on top, this is in the bottom. So basically, that is a way to compute RO bar. But then, if I want to understand what RO bar, what RO does, so if I want to compute RO and just do O as the origin, then of course it will have exactly the same formula. So, by the way, I can now check this property. So this property is something which one can check if one computes a composition of these two rotations. And one can easily see that what one needs to do, one needs to take first rotation, and this will be an application, this matrix multiplied by xy, and then when I compose it with the second, I need to take another matrix multiplied with xy, and this should be equal to the matrix for phi1 plus phi2 multiplied by xy. And this is indeed true, and actually this identity in matrix form is a statement that if I take a matrix cosine phi1 plus phi2 sine phi1 plus phi2 minus sine phi1 plus phi2 cosine phi1 plus phi2. I have minus here and minus there, but I can change signs of both angles and this will be fine. So that's the same as the matrix where I take cosines phi1, sines phi1, cosines phi2, sines phi2 times cosine phi1 sine phi1 minus sine phi1 cosine phi1, and here I do the same with phi2. And that's indeed true if you multiply matrices as the rule of matrix multiplication tells us. And this will give formulas for cosine of sum and sine of sum. So cosine of phi 1 plus phi 2 equals cosine phi 1 cosine phi 2 sine phi 1 minus sine phi 2. Okay. So that's a little discussion of how multiplication of matrices is related to isometries, and we will talk maybe a little bit more about that later on. My next goal is to discuss composition of rotations. Proposition, beautiful one. A composition of rotations is a rotation. Maybe moreover, angles add. So you might ask, but we already discussed that when we took a rotation by angle phi with the center O and by angle phi 2 with the center O, we compose them and check that this is a rotation with angle phi 1 plus phi 2. But the difference is that here I don't say that the centers are the same. So a general picture is I take rotation with the center O and phi 1, and it's O1, and rotation with the center O2 by phi 2. And the picture is kind of like that. So I have O1, I have O2, and I first rotate with the center O2 everything, and then rotate with the center O1, and its rotation with one center, another center, and it's not obvious at all that the composition is in a rotation. So actually, I'm sorry, so rotation is a rotation, let me say here carefully, or a parallel transport. Parallel transport and angles add. So more carefully, I'd say that if I take a rotation with angles phi 1 and phi 2, then it will be a rotation with a certain center O3, which is one can find, but it's non-trivial, and angle phi 1 plus phi 2 if phi 1 plus phi 2 is not equal to 2 pi k for some k. So because of course in this case it will be kind of a rotation with zero angle, which is kind of identity, but it won't be identity. So if angles add up to 2 pi k, then it's a parallel transport by a certain vector v if phi 1 plus phi 2 equals to 2 pi k, where for some point O3 and vector v. So that's the statement. And you might worry that that looks a little ugly, so sometimes you get parallel transports, sometimes you get rotations, but in general we'll also see that if you take a composition of a rotation and a parallel transport, that's also a rotation with a different center O prime by the same angle phi, and so parallel transports and rotations form a subgroup. So the subgroup has a name. So if I take all parallel transports and all rotations, this is a subgroup which is called isom plus of R2, and that's what's called orientation preserving isometries. Okay. Orientation preserving isometries, isom plus of R2. That's a subgroup of isom of R2. And actually I will talk about it a little later, but these are isometries you can do if you take your plane as a rigid thing and move. So in general, you might notice that in our definition, isometry is not a process. It's actually you take something, you move it, and that's the result. But some isometries you can do if you just slide your plane along itself. And if you take, for instance, reflection, you cannot do it. You need to take your plane and sort of move out of it and put it back down. And so these are exactly those which you can do by sliding it. And they are called orientation preserving for a reason we'll talk about a little later. So parallel transports and rotations. So let me prove this theorem, prove this proposition. So first observation, so let me assume that phi1 plus phi2 is not equal to 2 pi k. So assume phi1 plus phi2 is not equal to 2 pi k. I also assume phi1, phi2 are less than pi, just because I want to prove it with a picture, and one can also go through some other cases. So, of course, to be completely careful, one needs to prove like the statement without any extra assumptions, and it starts to be more simple to prove such things when you use something more algebraic than these geometric synthetic arguments, people say. And I will discuss later on a way to understand isometries with complex numbers. All these theorems will become extremely simple in this case. But right now I want to give these geometric arguments, and so I will make these extra assumptions which simplify things. So first I need to find a center. So I say that rotation, so the composition is a rotation with a certain center, so I better have a fixed point. So remark, a rotation with a center O by phi has a unique fixed point O, and for phi not equal to 2 pi k. So in the other case it's the identity. So let me try to find it after all. So that's not hard because I take O1 and O2. So I want to point that when I first move by phi2 and then move by phi1, I go back. So let me take a point in the following way. So I connect O1, O2 by a segment, and then I draw lines or rays with angle phi1 over phi2 over 2 and phi1 over 2. And this will be my point O3. And then if I do RO2 phi2 of O3, this will give me a point O3 prime, and this point is obtained by going basically by phi1 over phi2 over 2, and then phi2 over 2 again, and so this is the same thing as do a reflection with respect to this line. So this is O3 prime, but then as a simple argument, can show this angle will be phi1 over 2, and when I go by phi1 over 2 back, RO1 phi1 of O3 prime is again O3. So O3 is fixed. So now I know that my composition of rotations fixes O3, and then the question is why it's a rotation. So, and that's actually very simple, because if I now think about RO1 bar phi1 composed with RO2 bar phi2, which is of course exactly the same as what composition does to vectors, then when you compute composition applied to vectors, not points, you don't need to think about the origin. You can just, I mean, this bar map, which is a way it acts on vectors, does not depend on the choice of a point O1 at all. So that's actually the same as, so both of them are the same as R bar O3 with the same angle. Just because this point is not important at all, because I think at what rotation does with vectors, and I can always move them to any point and do it. So that's not important. And also we saw it when we draw a matrix, so the matrix was dependent only on the point O, on the angle, but not on the point at all. And so what it means that this is a rotation with the center O3. I compose them and they have now the same point, phi1 plus phi2. But what it means that my transformation takes O3, and if I take any point x, I know what I do. I need to rotate the point x by angle phi1 plus phi2 to get the vector O3 f of x. Let me call it. So this is x, and it goes to a map y, and I know that the vector O3x goes to O3y, and O3 is fixed, so vector O3x goes to the vector O3y, and O3 is fixed, and then of course what it means is x goes to y. And this means that my composition is a rotation with the center O3 by the angle phi1 plus phi2. Exactly this one. So that proves the theorem in this special case here. And everything else one can do in a similar way, but the pictures will be slightly different. So not only have I computed the angle of the composition of rotations, I also computed the center. So it's some point which forms this phi1 over 2, phi2 over 2 angles with a line O1, O2. And so now I want to formulate a theorem, which some people call Napoleon Theorem, but it's actually historically probably unrelated to Napoleon at all. That's a legend. But I'm going to prove a theorem, which is a beautiful theorem in geometry, and the proof uses this trick with composing rotations. Application. So theorem, which people at least call usually Napoleon Theorem. And it says the following. So I take a triangle ABC, and I will draw it acute angle triangle, and then let C1AB, triangle C1AB, triangle A1BC, triangle B1AC be regular triangles on its sides. So going out. So let me draw the picture. So I just construct this irregular triangles. This one is not very regular here. And let, so this is C1, and this is A1, and this is B1, and let me denote by OC, OA, OB their centers. So a regular triangle has a center, actually a center of symmetry, so OA, OB, OC are their centers. Their centers. Okay, so perfect. So then theorem says that the triangle OA, OB, OC is regular. So all angles are 60 degrees and so on. So that's a beautiful theorem. And the proof will be just a couple of lines using compositions of rotations. So proof. So let's consider a composition of 3 rotations. The proof is clever. It's not so easy to see where it came from. So first I do a rotation with the center, so it will be a composition of 3 rotations. And first I do composition with the center OA. OA by the angle 2 pi over 3, 120 degrees, then OB with the same angle, then OC with the same angle. So this is F. So by the previous theorem, so firstly, a composition is associative, I can put brackets as I like, and so angles will add up, and so the sum of the angles is 2 pi. So according to our theorem, F is a parallel transport. Parallel transport. But F fixes a point, because if I take F and apply it to a point B, then first I think what OA does to it, then so then it goes to sort of, first B goes to C when I do rotation with the center OA, and then it goes to A when I do a rotation with the center OB, and then it goes to B when I do the rotation with the center OC, and so this will be B. But F is a parallel transport, it fixes a point. So it means F is the identity map, because usually parallel transport doesn't fix a point, is the identity. So actually F does nothing, and so I have computed a composition, so I can say that F rotation, so I can multiply on the inverse from the left, and so what it means that rotation OB 2 pi over 3 composed with rotation OA 2 pi over 3 is a rotation OC, and the angle is minus 2 pi over 3, which is 4 pi over 3. That's the same thing. Perfect. But then I can draw a picture from the previous theorem. So I have this point OA, OB, and then, so angles of rotation are 120 degrees, 2 pi over 3, and so if I want to find a center, I need to take angles 2 pi over 6, which is 60 degrees, here 60 degrees, and this will be OC, because I know that this is a center. But that then angle OA, OC, OB is equal to 60 degrees, and so similarly for other angles between these 3 points, and so we see that triangle OA, OB, OC is regular. And that finishes the proof. It's a very beautiful argument, quite non-trivial. Okay, so basically what I used again, I looked at 3 special rotations, found their composition, but then there is another way, like by a pure salt argument, but then there is another way, which is this recipe which we discussed, and when you compare these two, you see that the angle OA, OC, OB is 60 degrees, but then similarly all other angles are 60, so the triangle is regular. Okay, so next question I want to talk about is the classification of isometries. So one can ask, what isometries are there? And a priori, that's quite a non-trivial question, because, you know, we have different kind of isometries. We have parallel transports, central symmetries, rotations. And if you start composing them, a priori you expect that you will get a wild number of possible things you can do with a plane. But from this theorem, which we discussed a couple of minutes ago, when we compose parallel transports, rotations, central symmetries, we will get again parallel transports, rotations, central symmetries. So central symmetries are rotations, so just parallel transports and rotations. And even if you compose 100 different rotations with different centers and certain parallel transports in different directions, the composition will be just one unique transformation, which is either a parallel transport or a rotation. And so in a sense, just there is nothing else. And of course, we also have reflections, and one can try to add reflections. And basically, the theorem we are going to prove next time, which is called Schall's theorem, is a theorem which classifies all isometries. I will just say that every isometry is either a parallel transport, or a symmetry with respect to a line, or a rotation, or something called sliding symmetry. It's a symmetry plus parallel transport in the direction of its axis. And this is a theorem I'm going to prove.